Welcome to this section on magnetic flux control. First, what is magnetic flux control? In this course, magnetic flux control is a generic term for modification of induction coil magnetic flux by means of installation of magnetic templates, or magnetic flux controllers. Magnetic flux control, due to application of non-magnetic bodies, or Faraday rings, also known as flux robbers, is not considered here. Magnetic controllers may significantly change magnetic field pattern and coil parameters. Their application must be considered as part of the whole induction system design. Because controllers play different roles, like magnetic flux concentration, shielding, and distribution, they are also called concentrators, cores, or shields, depending on application. In many cases, controllers fulfill several functions simultaneously. Effects of magnetic flux controllers on OD coils. The role of magnetic flux controllers and their effects may be explained and evaluated by composition of magnetic flux circuit similar to electric current circuit. Magnetic flux causing heating is equal to ampere turns of the coil, driving force of magnetic flux, divided by total magnetic resistance of the circuit. It is a sum of magnetic resistance of the active zone, Zm, and magnetic resistance of the return path, Rm. Applying controller on return path, we strongly reduce Rm and therefore increase magnetic flux with the same coil current or reduce current demand for the same flux. Effect of the controller is higher when Rm is high compared to Zm. Improvements expected for OD coils. Improved heat pattern control and/or ability to heat difficult areas, axle fillet, etc. Better utilization of power in workpiece for short static coil, energy savings up to 30%. Lower coil current and therefore reduced losses in supplying circuitry, transformer, capacitors, buswork. Shielding of part and machine components from unintended heating. For long OD coils, there is a small coil parameter improvement. However, in some cases, magnetic controllers are required for local temperature control and shielding. Heat treating of some difficult parts cannot be achieved without application of flux controller. Melting inductor for glove box environment. Induction coil for melting of radioactive materials in protective atmosphere. Here we see an example of shielding effect and efficiency improvement. Fluxtrol A shields on the side and bottom coil surfaces allowed to strongly reduce losses in the chamber walls and bottom plate. Increase the furnace volume in the same chamber. Increase coil efficiency from 23 to 63% due to reduced losses in chamber walls, bottom plate, and in the coil. Effects of magnetic flux controllers. In ID coils, magnetic flux must return back around the turns in narrow space inside the coil, and therefore magnetic resistance, Rm, is usually high. Concentrator, core, dramatically reduces coil current required to push the flux on return path. When the core is installed, magnetic flux and power are much higher with the same coil current, or current demand is much lower for the same power. Improvements expected for ID coils. Shorter heating time. Substantial energy savings, oftentimes 40 to 50% or more. Strongly improved electrical efficiency. Drastically reduced current demand. Reduced losses in power supplying circuitry. And heat pattern control.